Well, let's go to another speaker, the next one, which is Dr. Diego Kaski. Professor Diego Kaski is an international leader in vestibular neuroscience with important publications in many journals. And he's the director of the Center of Vestibular Neuroscience and Behavior of National Hospital for Neurology and Neurosurgery, an associate professor of the University College in London, England. Okay. We had this conference recorded.
So it's once again a real pleasure to be part of this joint venture between Latin American Neurotology and the Forum for Indian Neurology and Education. I'm going to be focusing my talk today on artifacts in oculography, with a focus on transmitted eye movements and the concept of pseudonystagmus. For many of us who have been working in this field, I think the concept of eye movement recordings, which may perhaps sound quite simple, is indeed a very complex art. And the more one does this, the more one realizes that there are a number of potential artifacts that one might encounter when recording eye movements, and that any eye movement recording has to be very carefully thought about and planned. There are, I think, now a number of different types of eye trackers, and there has been a huge growth in the nature and number of studies that have begun to explore eye movements across a field of healthy controls, but also patient populations. And I think it becomes increasingly important to understand some of the drawbacks in eye movement recordings, but also ways in which that can be facilitated to get the most out of the recording and avoid misinterpretation of data. I'm going to focus on this specific issue in relation to a study that was done in patients with Parkinson's disease some years ago now, that I think highlights many of these difficulties that we often come across in eye movement recordings. Eye movement recordings have been done for many, many years, and the techniques have certainly evolved over time. And in its simplest forms, one can either take stills of the eyes, there can be video recordings of the eyes, or more invasive techniques that will explore eye movement in much more detail, such as scleral coil techniques. I'm going to start with this finding that was almost lost in the literature, I think, for many years, by Deval and Buta in 1998, who studied just a handful of patients with Parkinson's disease and identified that these patients had an instability in their eye movements during steady fixation. And the instability in the eyes was depicted in these figures here. These are just two of those subjects that were used to show that there seems to be an oscillation of the eyes in patients with Parkinson's disease that mirrored to an extent the oscillation that was occurring in the limbs of these patients, the typical tremor that that patients with Parkinson's disease often manifest. The feature about the findings from this particular study that are most salient is that these oscillations in patients with Parkinson's disease tended to be uniocular, just affecting one eye primarily. And this was something that was difficult to account for the authors in the study, but they nonetheless discuss how perhaps there is some relationship between the limb tremor and the eye tremors in patients with Parkinson's disease, and they use this concept of an attractor effect, where the movement of the limbs may somehow be transmitted to the movement of the eyes. And the reason and rationale behind this was because the arm tremor and the eye tremor tended to have similar frequencies. This was, I think, seized upon by Gitchell and colleagues in the States in 2012, and they carried out a much larger study in patients with Parkinson's disease, in fact 112 patients, and reported a curious observation that they termed a pervasive ocular tremor across all of the patients that they studied. Indeed, given that every single patient that was looked at in this study had this abnormality, they quite rightly put this forward as a potential biomarker for Parkinson's disease. So I thought we'd maybe just touch base and take a step back and think a bit about steady fixation and how that is achieved, and indeed what types of eye movements can interfere with steady fixation. So in order for us to see a target clearly when we're looking straight ahead, the target must be held in the fovea, and the image ideally mustn't move. Any movements beyond approximately 5 degrees per second over the retina will induce a slip of that image in the retina and therefore move the image away from the fovea and therefore result in disturbed vision that we typically associate with oscillopsia. There are two ways in which steady fixation can be disrupted. If the head is fixed and we're thinking just about the eye movements that occur, then there are three major types of eye movements that can interfere with steady fixation. And those are micro tremors that are typically very high frequency, 70 to 100 hertz, and tend to be very, very small in amplitude, usually subclinical in terms of their detection. There are microsaccades that have a much lower frequency and a slightly larger amplitude, typically 1 to 2 hertz and less than 1 degree. And these are thought to allow us to prevent the retina from saturating from an image, and therefore allows us to continue to see that image when we're looking straight ahead. And then there are ocular drifts that are extremely slow drifts of the eyes that again typically will not interfere with vision in healthy individuals. If one tries to stare at a stationary object and the head is free, then there is an additional requirement for ocular motion to stabilize the vision. And this is the remit of the vestibular ocular reflex, and can be viewed in a sense like the brain's Steadicam. So for every movement of the head in one direction, the eyes will move in the opposite direction at that same speed in order for the image to remain on the fovea. So this pervasive ocular tremor, I thought we could look at this in a bit more detail and see what they found. So this was an oscillation that had an average fundamental frequency of approximately 5.7 hertz and was well within the range of the limb tremor that is typically observed in Parkinson's disease, typically 4 to 7 hertz. It had a small amplitude in the horizontal plane of less than 0.3 degrees and a mean vertical amplitude of about 0.3 degrees also. They evaluated the potential for head movement in a subset of individuals, about 60 individuals with Parkinson's disease, using a position tracking device, and they didn't find any evidence of a head movement in these patients, even though the head was not formally restrained. So the nature of the ocular tremors that were observed in these patients doesn't really fit with a microtremor, microsaccade, or even an ocular drift, which begs the question, what kind of eye movement could this represent? This is a figure taken from that original paper by Gitchell and colleagues that looks at a number of individuals with Parkinson's disease. Two here, different patients who are medicated for Parkinson's disease with levodopa, and in the last figure here, there's a patient who's unmedicated, and the top one here is a control. The black traces are the eye movements, the red traces are the head movements, and this is a 1.2 second recording, which unfortunately is quite brief in order to ascertain the exact nature of this. But you can see that there is a tendency for an oscillation of the eyes over this 1 second recording, with an average frequency of 6 for the top trace and a little higher frequency for the bottom trace, about 10 hertz. So is this a pendular nystagmus? Perhaps that's what is inducing the eye movement in these individuals. Well, actually, there are a number of features that would point against that. Firstly is that these are smaller amplitude in waveform than those that were reported in the PD patients. The phase of the oscillations in pendular nystagmus is typically reset by saccades. And this is something that was looked for in this particular paper and was not found, again, arguing against this being related to pendular nystagmus. And perhaps the most important feature is the absence of any oscillopsia. So most of you will know that a patient that develops acquired pendular nystagmus will tend to report quite prominent oscillopsia in the plane of that oscillation, contrary to what you might expect in someone with a congenital type of oscillopsia or pendular nystagmus. So we try to characterize the nature of that pervasive ocular tremor, admittedly in 2 individuals as opposed to 112. But I think that the methodology that we employed, I think, takes into account some of the difficulties in oculomotor recording. And I think is a good example of the sorts of issues that one has to think about. So we used 2 different kinds of eye trackers just to see whether there was indeed a difference in these in different patients, and we simultaneously recorded the head and the eye movements. The patients were typical patients with idiopathic Parkinson's disease. They had DAT scans confirming the abnormalities in dopaminergic uptake, and had scores of UPDRS done prior to the recordings. We used 2 kinds of head movements trackers. So one is an accelerometer, which is an Android application that was attached directly to the head-mounted eye tracker. And in the second, we used an analog linear accelerometer, which is also triaxial. And we used both a mobile eye tracker, in this case was the iBrain eye tracker, and an infrared scleral video oculography, which many of you will be familiar with. This is what we found, and this is a representative trace in the first individual. The eye trace here in the top, the head trace in the bottom. There are 3 segments here, and I'll talk you through each of these. So this is where the head was allowed to oscillate freely. This is when the head was manually restrained in between the examiner's hands, and this was when the head was again released from the manual restraint and was allowed to oscillate. This is a 20-second recording of the procedure, and you can see that there is an oscillation of the eyes, as was reported in the paper by Glitchell, when the head is free, and there's an accompanying head oscillation here. When the head is restrained, we see an absence or reduction of the eye tremor, and then as the head is released again, this re-emerges. So in our case, we saw a pretty tight coupling between head oscillation and the eye oscillation, and this led us to look in a bit more detail at the nature of the oscillation of the eyes and the head. And what one can appreciate here is that the eye oscillation and the head oscillation are in antiphase to each other. So as the eyes move in leftward, the eyes move in a leftward direction, the head is moving in a rightward direction. There is also a very tight correlation between the head and the eye movements. This is in dashed lines, a co-registration of the 2, and you can see that they're very tightly coupled. We looked also at the oscillation of the limbs in addition to the head to see whether there was some relationship, as was originally described in 1998, between the limb tremor and the eye and head tremors. And again, we see a very tight relationship between the amplitude and frequency of the head and limb oscillations. So what does this tell us? Well, this tells us that somehow the eye oscillation is tightly related to the head oscillation. And yet that seems counter to what was originally described in those sub-cohort of individuals in the Glitchell paper, where no head movement was recorded. And so we wondered whether perhaps the absence of any head movement in the 112 patients was related to the way in which the head movement was recorded in that paper. So we sought to compare a magnetic tracker, which is designed for position, versus an accelerometer, which is of course designed to detect acceleration. What I'm going to show you here is a single patient again, in whom we recorded the hand acceleration and the head acceleration using an accelerometer, and the position of the hand and the head using a fast track magnetic tracker. And what you hopefully can appreciate is that there is a pretty prominent acceleration of the limbs in this patient with a corresponding smaller amplitude acceleration of the head. That is also detected in the hand with a fast tracker, but there appears to be no signal at all, and this is sort of noise primarily when one uses the magnetic tracker for the head movements. And this is in part related to the amplitude of the stimulus that's being recorded. So this is another example of the difference between the accelerometer and the fast track, focusing specifically on the amplitudes that we're talking about in relation to a small head tremor. So the above trace is the accelerometer. This is the fast track. When they're both mounted on top of a shaker, that we gradually increase the frequency of and its amplitude and gradually decrease its frequency and amplitude. And what one can appreciate is, if one looks at these very small ranges of movement and frequencies, is that the accelerometer is able to catch some signal with very minor movements that the fast track cannot, suggesting perhaps that in the 112 patients where no head tremor was reported, that the reason that this was the case was because of the techniques used to capture the head movement that were insufficient really for that small degree and frequency of movement. And this concept is not really a new one. It has been shown before. This is an example by Adolfo Bronstein in a patient with bilateral vestibular failure and a concurrent head tremor, that this induces quite significant oscillopsia in these patients. So if we think back to the relationship between the VOR and the eye movements, if one has failed to induce a VOR response in relation to a head tremor, then the eyes will be deviating left and right, and that will cause oscillopsia. Whereas if one has an intact VOR and there's a head tremor, that should not impact on steady fixation. So this particular patient here had a clear oscillation of the head when it was unrestrained, and you can see the acceleration profile here. So quite a large acceleration, but small amplitude movement. And this induced in the patient quite severe oscillopsia. And the head tremor, of course, would be here in the same phase as the eye tremor. So the eye and the head would be doing similar things. And when the head was kept still, there was no further oscillopsia. So this really mirrors the findings that we had, where the presence of the eye oscillation was tied in specifically to the head oscillation, and that head oscillation appears to have been coming from a transmitted tremor of the limb. So the rest tremor in the limb was being transmitted through the axial structures into the neck. And that was inducing a small head tremor, and this was inducing a VOR response, which is what was recorded in our two patients. And we wonder whether a similar mechanism may underpin the pervasive ocular tremor that was identified in patients with Parkinson's disease. And we have several reasons to suspect that that was the case, and there has arguably been a lot of controversy surrounding that paper. I haven't included here the full rationale, both for and against the argument of pervasive ocular tremor, but suffice to say that it is a good example of how difficult eye movement recordings can be in a patient population like Parkinson's disease, and the real need to think very carefully about what the eye movements are telling us and ensuring that we're cutting out any potential artifacts from head movement. There is, however, something important that probably still needs to be better defined, and that is that many patients with Parkinson's disease report an internal tremor, and it seems, perhaps, based on some preliminary EMG findings, that there may be some subclinical tremor in these individuals that can be picked up and perhaps is being transmitted all the time. And therefore, the possibility that there is a pervasive ocular tremor in these individuals, again, related to a transmitted tremor, is still there. And I think that there still needs a bit more work to be better defined. So just to summarize the key findings, the pervasive ocular tremor, in our opinion, is a compensatory eye movement secondary to the transmitted head tremor. The key points of evidence for this are that the eye velocity is completely out of phase, 180 degrees out of phase with the head velocity, as you would expect for a VOR response. It can be suppressed during head restraint, and the eye oscillation correlates very strongly with the head movement. So it is possible that mechanical transmission of a tremor can occur from one limb to other body segments, including the head, although head tremor per se is not thought to be a common feature of Parkinson's disease. If there is a rest tremor that is being transmitted, then that potentially may be one mechanism. And I guess we would argue that this mechanism is more likely than an independent tremor generator in the eyes. The frequency and the amplitude of the ocular tremor that was reported in the 112 patients, one would expect would induce oscillopsia, and this is not something that has been reported in Parkinson's disease. And perhaps most saliently from our perspective, even if the amplitude of the oscillation is too small to be seen with the naked eye, a continuous oscillation in the eyes of about 5 Hertz, as was reported, would be clearly identified by direct endoscopy that magnifies the retinal structures by about 10. And this again is something that hasn't been reported, and we have not directly observed in any patient with Parkinson's disease. So just to summarize, I think there are a number of eye tracking requirements that will undoubtedly be important to bear in mind when doing research of this nature. One, first of all, needs quite high resolution techniques, such as the traditional scleral search coils, which are invasive, or more recent infrared eye tracking or video oculography techniques. The second is that it's important to consider the contribution of the head to any eye movement, and therefore the head has to be immobilized, either using a custom-made bite bar ideally, or indeed the eye tracker should be insensitive to movements of the head. And this is something that is now a pretty standard feature in many head-mounted eye trackers. There has to be some sort of simultaneous recording of the eyes and head, and ideally also of the distant limbs. And this means that the different devices have to be correctly calibrated, and that the signals have to be acquired in synchrony. And finally, the tremor recording of the head and limbs should ideally be done using gyroscopes or accelerometers rather than position trackers that are much less sensitive for small amplitude and low frequency movements. So I'm going to finish this brief talk here, accepting that there are numerous additional artifacts that are encountered in oculomotor recordings that are, of course, beyond the scope of a brief talk. But I really wanted just to focus on the importance of VOR considerations in the context of eye movement recordings. And given this high-profile publication in Archives of Neurology, that, in our opinion, seems to have been describing an artifact of the VOR rather than a true oscillation of the eyes in patients with Parkinson's disease. I am, of course, very open to receiving questions, and that can be done directly via the forum or indeed emailed to me personally. I'm happy to respond. Thanks again for your attention.